Okay, let's start. Good evening, everyone. My name is Yoshinori Matsunobu. I'm working as a MySQL consultant at Sun Microsystems now in Oracle. So let's start Linux performance tuning and stabilization tips session. So this is today's agenda. Okay. The session consists of 3 parts. So part one is memory and swap space management. The second part is synchronous I/O and file system and I/O scheduler. The third part is useful commands and tools like iostat, tmpfs, and SystemTap, GDB, etc. Okay, let's start with memory management. So random access memory is the most important hardware component for database servers. Why? Because random access memory's access speed is much faster than storage like hard disk drive and SSDs. So random access memory's access speed is nanoseconds order. So 100,000 queries per second is not impossible, especially if it is in-memory select private key lookup statements. Hard disk drive's access speed is milliseconds order, so say 5 milliseconds or something. And SSD's access speed is microseconds order, so they are much slower than random access memory. And currently, 16 to 64 gigabyte RAM is not pretty common. So, hot application data should be cached in memory to boost performance. And minimizing hot application data size is important to cache as many data as possible. So say, for example, use compact data types like small int instead of varchar deep int, or using timestamp instead of date type, etc. And do not create unnecessary indexes or date records or move to archive tables to keep tables smaller. So this is an example about how throughput changes by increasing memory. So this is a DBT2 benchmark, light intensity benchmark. And the hot data size is about 20 to 25 gigabytes. So when buffer pool size is 1 gigabyte, throughput is only 1,100 transactions per minute. But increasing to 2 gigabytes, the throughput increases to 1,800. And by increasing to 5 gigabyte, TPM improves to over 4,000. And then, if all data is cache, the throughput becomes 36,000 TPM. So, memory size is very important. Of course, for select, memory is very important, but also for insert or update or delete, memory is very important. Why? For example, for insert, when executing insert statements, random reads and writes happen when inserting into indexes in random order. And update or delete, when update or delete statements, random reads and writes happen when modifying records. Okay. So not only for selects, but also insert, updates, deletes, memory size is very important. To highly utilize memories, direct I/O is very important. So buffered I/O requires file system cache. For example, when accessing to data file, in a data file, the data is first cached in file system cache, then loaded into buffer pool. So it's duplicate cache, not efficient. By using direct I/O, it bypasses file system cache, so it can fully utilize memory. In InnoDB, by setting InnoDB flash method for ODirect, direct I/O can be used. But not all files can use the direct I/O. So to use a direct I/O, file I/O unit must be a factor of 512 bytes. So we can't use ODirect for InnoDB log files or binary log file, MySQL, or Postgres data files. These files are not aligned, so we cannot use direct I/O for these files.
So the 512 bytes?
Right.
There is a change going on to change the sector size to 4K?
It depends on kernel. So as far as I know, so it is hard coded.
Right, so it's
yeah.
Okay, interesting.
So to highly utilize memory, so people might want to allocate as many memory as possible. But of course, we cannot use memory more than physical memory size. So this is an example. This machine has 32 gigabytes memory, and I allocate the buffer pool size to 35 gigabytes. But we cannot allocate 35 gigabytes memory for because the physical memory size is limited. What happens? In this case, we cannot allocate 35 physical memories, so we can only allocate the limited number of memories. So, of course, Linux kernel and other background processes allocate memories. So, in this case, the physical memory for MySQL was 30 gigabytes. So, only 30 gigabytes were allocated to MySQL. So, what about the remaining 5 gigabytes? It was swapped. So what happens if no memory space is available? So Linux takes two actions. The first one is reducing file system cache to allocate memory space. At the same time, Linux swaps processes to allocate memory space. So in this case, about 5 gigabyte swap happened. Of course, swap is bad. Why? The process spaces are written to disks when swapped out. And disk read happens when accessing to on-disk process space. This is called swapping. So both random reads and writes happen. This is very inefficient. So swap is very bad. So sometimes people ask, what if setting swap size to 0? So it is possible to set swap size to 0 on Linux. Then swap doesn't happen anymore. But this is very dangerous, so don't do that.
Why?
So when neither random access memory nor swap space is available, OM killer, OM means out of memory killer is invoked. And OM killer may kill any process to allocate memory space. So, and the most memory consuming process, so this is MySQL, will be killed at first. So this is a both shutdown. So crash recovery takes place on the start. And priority is actually determined by order by, block, PID, OM score, descending order. And OM score normally MySQL has the highest score. OM score depends on virtual memory size and CPU time and running time, so various components, but mostly determined by virtual memory size. So MySQL has highest virtual memory size, so this is killed at first. Not only MySQL will be killed, but also it takes very long time for OM killer to kill processes. So, for example, so minutes to hours, it takes minutes to hours to kill processes. So we cannot do anything until enough memory space is available. So here is an example. So setting swap size to 0 and trying to allocate 32 or more memory space for MySQL. But only 32 gigabytes physical memory is available, and Linux kernel also uses memory. So MySQL cannot allocate more memory, more than 30 gigabyte memory. So no memory space is available. So OM killer was invoked in this case. But in this case, it was not killed immediately. It took 30 minutes to kill MySQL. During that time, the system resource was stick to 25%. 25% seems moderate, but this is a 4-core machine. And single core used 100% system resources. So actually this was a CPU bound workload. And terminal freezed at this time. So I can't take any actions. I can't even establish SSH connections. So in this case, more than 30 minutes, MySQL was hanged and no action was taken. So application cannot respond for 30 minutes. So swap is bad, but OM killer is much worse than swap. So what if stopping OM killer? So if proc PID OM adjustment OM ADJ is set to -17, OM killer won't kill the process. So setting -17 to SSHD is a good practice so that we can continue remote logging. But don't set -17 to MySQL, right? If our over-memory consuming process is not killed, Linux can't have any available memory space forever. So we cannot do anything for a long time. I tested before coming to the user conference, so I tested this in Tokyo and took an 8-hour flight to San Francisco and arrived there. When checked, it was hanged at that time. So it took hanged over 10 hours. So I forced to power off my Linux machine and restart it. So don't set -17 to MySQL. So swap space is absolutely needed to stabilize these systems. But we do not want MySQL swap that. So we won't prioritize MySQL. So what actually consumes memory? So of course, database server, MySQL consumes memory. Mainly process space is used in the daily buffer pool, key buffer, sort buffer, etc. And sometimes file system cache is used, MySQL files, or in-daily log files, etc. And also administration, such as backup, cache requires file memory. So mainly file system cache is used. In this case, we want to keep MySQL in memory rather than allocating large file system cache. Because backup is one-time operation, so it is not needed to cache for a long time. So be careful about backup operations. This is an example. So the upper graph, this is a 27 gigabyte MySQL memory, and all memory was resides in memory. I copied 8 gigabyte data files. Then swap happened. So about 5 gigabyte memory space was swapped out. So copying large files often causes swap. So you need to care about backup operations. What can I avoid swap? So setting VM swapness to 0. This is a good practice. So by setting VM swapness to 0, when physical memory space was fully consumed, Linux kernel reduces file system cache with high priority. So lower swapness increases priority. So by setting swapness to 0, Linux kernel always reduces file system cache before taking swap, doing swap. So even though I copied 8 gigabyte data files, almost no swap happened. So all memory was residing in memory. So after no file system cache is available, swapping starts. So if I allocate 35 gigabyte memory space in MySQL, then swap starts. This is much safer than OM killer because swapping doesn't mean MySQL crash. So it doesn't mean MySQL doesn't hang for a long time. So swap is bad, but it's much safer than OM. So general recommendation is using ODirect and allocating enough swap space and setting VM swapness to 0. Okay, let's go to the next topic, it's memory allocator. So MySQL uses mroc or mmap for memory allocations. It depends on OS. So by default it uses glc mroc. But faster, more concurrent memory allocators such as tcmroc can be used. So install Google Path Tools, which includes tcmroc. So then install Google Path Tools. Then export lb preload equal user locally tcmroc underscore minimal.so. Then MySQL detail. Then it automatically uses tcmroc. InnoDB internally uses its own memory allocator, but this behavior can be changed in InnoDB plugin. If InnoDB uses SystemRoc that is set to 1, this is default. InnoDB uses OS memory allocator, so tcmroc can be used by setting LD preload. So Memory allocator would matter for CPU bound workloads. There are many folks did benchmarking, say sysbench read-only benchmarking and other benchmarking. This is the DBT2 benchmarks. When the server is disk I/O bound, no difference, because this disk I/O bound, so memory allocator difference is negligible. But when it is CPU bound, memory allocator might matter. In this case, about 4.4% improvement per bound. And be careful about per session memory. So this is general recommendation. So do not allocate much more memory than needed, especially for per session memory, right? Because the swap or OM killer is dangerous. Not only for that, but allocating 2 megabytes takes much longer than allocating 1 to 8 kilobytes. So Linux malloc internally calls BRK system call if size is less than 512 kilobytes, else calling mmap. Mmap takes much longer time than BRK. This is the example. In some cases, too high per session memory allocation causes negative performance impacts. Select asterisk from huge MySQL table, limit 1. When setting read buffer size equal to 256 kilobytes, only 0.68 seconds took to run 10,000 times. But when setting 2 megabytes, over 18 seconds took to run 10,000 times. So this is much more inefficient. In many cases, MySQL does not allocate per session memory than needed, but be careful about in some extreme cases. In this case, using MySQL and limit and full table scan. In this case, per session memory matters significantly. Okay, let's go to the next topic. So file IOs, synchronous IO, the file system, and IO scheduler. File IO and synchronous writes. So database servers calls fsync many times per transaction commit or checkpoints, etc. So fsync is very expensive, but can be significantly faster by using write cache protected by battery. So without battery, every time when you commit, the disk seek and rotation happens. So this is very slow. So probably less than 200 on hard disk drive. But when you have write cache with battery, transaction commit finishes by writing to cache. So you can cache 10,000, more than 10,000 fsyncs per second. Then hardware RAID controller can write all of cache information to disks at one time. So this is very efficient. And disable write cache on disks for safety reasons. On Linux, many cases write cache is enabled on storage, but this is dangerous. So enable write cache on hardware RAID controller and disable write cache on disk. So you can gain more than 10,000 fsyncs per second with safety. And do not set write barrier on file systems. This is enabled by default in some cases. What is write barrier? This is writes through to disks even though write cache is enabled. So this is very slow, probably less than 200 things per second. On ext3, mount -o barrier equals 0, and xfs mount -o no barrier. On DRBD, setting no disk barrier in DRBD.com. So these are important parameters. And overwriting or appending, this matters. So some files are overwritten and others are appended. So overwritten means file size is not changed. And files, when appended, file size increases. So overwritten file is, for example, in the log file, this is overwritten. And binary log file is appended. On Linux and other many operating systems, appending plus fsync is much slower than overwriting plus fsync. Right? Because additional file space needs to be allocated and file metadata needs to be flashed per fsync. So this is very slow. When I tested, I got more than 10,000 fsync per second for overwriting, but I got only 3,000 or less fsync per second for appending. This depends on file systems, but including ext3, xfs, razorfs, I got only 1,000 or 2,000 fsyncs per second on bending. But copy and write file systems, such as Solid ZFS, is fast enough for bending. When I tested, I got over 7,000 fsyncs per second. So be careful when you using sync window equal 1 for binaries. So by default, it is 0. So this not fsync is not called. But when setting sync window equal 1 for safety reasons, fsync is every time when doing transaction commit, fsync is called and appended. So this is very slow. So if you really want to use sync window equal 1, consider using ZFS. And we are also working for pre-allocating window feature. So pre-allocates binary logs 1 GB beforehand, like in the log file, then overwriting the window. This should be much faster. And do not extend files too frequently. For example, in maybe auto extend implement to higher. So quick file IO health check example. So checking battery backup write cache is enabled and write barrier is disabled. So many times I see that people do not set write cache correctly. So checking is easy. So run MySQL Strap insert test. This is supported in 5.1. In daily single threaded and setting in flash log at TLS commit equal 1. Then every time when MySQL Strap execute insert, it is written to disk. In this example, MySQL Strap executes 100,000 inserts and pack with and auto-committed mode. So QPS should be over 1,000. If it is on, QPS is less than 100 or 200, there are some problems on write cache, so you should have a problem to check that. And sometimes buffered and asynchronous writes causes problems. Most of files are unbuffered, so direct and synchronously written on database servers, but some file I/O operations are not direct I/O and not synchronous. For example, file copies like backups, MySQL, MySQL dump, InnoDB flash log at TLS commit equal to, etc. In this case, data is not written to disk immediately, and the data is 30 pages are written to file system cache. Then, in the end, 30 pages are flashed to disks later. So on Linux, PD flash daemon takes care of it, and maximum 8 threads run to flash 30 pages. When 30 pages are flashed, highly depending on kernel parameters, especially VM-30 background ratio and VM-30 ratio. So flashing 30 pages starts in background after reaching 30 background ratio multiplied by run. So default is 10%. So if you have a 64 GB memory, so after 30 pages reaches 6.4 GB, the background PD flash 30 page flashing starts. And forced flash starts after reaching 30 ratio multiplied by run. So this 30 ratio is default is 40%. So about 25 GB, 30 pages, then forced flash starts. But forced and burst 30 page flashing is problematic, right? Because all buffered write operations then become synchronous. So every time when you write with buffered asynchronous writes, it is kept waiting for written to disks, which hugely increases latency. So you will be very disappointed about performance. So general recommendation is to flash 30 pages aggressively. So execute sync, the sync command by doing massive write operations like taking backups, or reduce VM-30 block, 30 background ratio. So, on Linux 2.6.32 kernel, PD flash was improved. Then on this version, PD flash threads are allocated per device. So flashing to slow devices won't block other PD flash threads. So these are the general recommendation for flashing type of pages. Okay. The file systems. So as Thomas and Mark Callaghan mentioned that the Facebook moved from ext3 to XFS. So ext3 is by far the most widely used file system, but not always the best. So one typical problem is deleting large files takes long time. So it internally has to do a lot of randomness, so it takes long time, especially on hard disk drive. In MySQL, if it takes long time to drop table, so all client threads will be blocked to open close tables by block open mutex. So this is really problematic. So be careful when using MySQL in a daily file path table or PBST or other storage engines. And writing to a file is serialized. So ext3 has imutex object per inode, and this is serialized when writing to a file. So sometimes it's faster to allocate many files instead of single huge file. This is not so many serious on hard disk drive, but this is serious for faster storage like Fusion IO, PCI Express, SSDs. Another typical parameters use dir index to speed up searching files and use barrier 0 to stabilize. XFS is my favorite file system. So fast for dropping files and concurrent writes to a file is possible when using direct. Actually, not officially supported in current RHEL. Red Hat Enterprise 5.4 support has XFS as a preview, but in the near future it will be supported. And SUSE Linux officially supports XFS. And typical configuration parameter is disable write barrier by setting no barrier. Yes.
Does Oracle Linux support XFS?
I don't know.
What's that?
I don't know, sorry. So ext2 is faster for writes because ext2 doesn't support journaling. It takes very long time at SCK, but I have some people deploy ext2. Is there anybody use ext2 in server? Oh. So on active redundancy environment, in some cases ext2 was used. My friend in Japan deploying web service, he's using ext2. It's dangerous. So I like XFS. Butterfs is under development. It's copying on write file systems, so supporting transactions and snapshot backups with Nova. Okay. So this is concurrent write benchmarks. I will talk about SSDs in depth on Thursday, 2 p.m. If you guys are interested in SSD topics, please join my session. This is one of the slides from picked up the SSD slides. This is a concurrency test. On hard disk drive, the concurrency doesn't matter on random write IOPS test. So when tested on one iOS thread or 100 iOS threads, the IOPS was not so different. Not different either on XFS. On Intel SSDs, the difference is a bit improved on XFS, but almost the same on XT3. On Fusion IO, it dramatically scales by using XFS. So it becomes 1.8 times better on XFS, so concurrency is improved. But on ext3, since write IO to the same file is serialized, so concurrency is broken. So IO scheduler. So actually, database server also schedules IO requests. So theoretically, Linux IO scheduler is not needed. But Linux has IO schedulers to efficiently handle lots of IO requests. On Linux servers, IO scheduler type and queue size matters. And Linux started from 2.6.10 RHEL 5 supports 4 IO schedulers. The most recommended IO scheduler is NURP. Actually, it does nothing except for sorting incoming IO requests by logical block addresses. That's all. Deadline is also good scheduler. So deadline prioritizes these requests rather than light async requests to some extent. This is to avoid light starving these problems. So if buffered and asynchronous are so many light requests, then light starts these, so we cannot release operations very well. So deadline takes care of it. CFQ is a default scheduler. So CFQ fairly schedules IO requests by IO thread. And anticipatory was actually removed in latest kernel. So what scheduler is going to use it? So default is CFQ, but CFQ sometimes worse than move for deadline. So you can change IO scheduler by execute echo move related to sysblock st something and q scheduler. So here is a typical benchmark to repeat why CFQ was bad. CFQ is bad. So running two benchmark programs concurrently. So one is a typical randomly simulated database reads. So multi-threaded random disk reads. And the other is single-threaded overwriting everything. So simulating redo log writes. So when no write happens, no difference was found. So both CFQ deadline, CFQ, there are no difference. So thanks to RAID and command queuing, it scales well on reads. But when you start fsync and write benchmarking, CFQ performs poorly. So when using NOC on deadline, write per second is great. So I got 14,000 IOs per second on everything. As I said before, so write IO pace is often very high because high disk and write cache can handle thousands of transaction minutes per second. So 14,000 write per second is not uncommon. Yes.
Okay, now just tested on attached drives.
Late, so
you tested this on any kind of a SAN, like attached to?
I haven't tested on SAN, but I tested on SSDs and hard disk drives. On CFQs, write IOPS was adjusted to read pass thread read IOPS. So in this case, one reader thread got to 200 IOPS, then it was almost equal to the write IOPS was degraded to this 226. So write IOPS was reduced, so which reduced total IOPS significantly. So I repeated this on SUSE and RHEL, so probably you can do it. So this syndrome affects on MySQL workloads. So this is a bit old benchmark, so tested on within in the 5.1 on how layer 10 and layer 5 environment. On loop and deadline, I got pretty well numbers, but CFQ performed worse than deadline loop. In this case, about 28 to 30% worse performance than CFQ deadline loop. So it is generally recommended to use loop was deadline. Okay, changing IO scheduler queue size. So what is a queue size, IO scheduler queue? So IO scheduler queue sorts outstanding IO requests to optimize disk 6. So by setting queue size to n, sorting n outstanding IO requests to optimize disk 6. So MySQL does not optimize IO requests internally, so it's highly depending on OS and storage. So when inserting indexes, passing disk writes and reads will happen. So by increasing queue size, Linux IO scheduler can sort outstanding IO requests by disks to minimize disk stick overhead. So this is a example graph. So time to insert 1 million records on hard disk drive. The horizontal line is existing records. By increasing existing records, random read will happen. So the gradually performs poorly. But if setting queue size by default, at the beginning, performance was very poor because a lot of random writes happens from the beginning. And since no optimization happened, so a lot of random disk seeks happened in this benchmark. So So by increasing queue size, you can minimize such overheads. But this optimization has no impact in InnoDB, because InnoDB and other many database servers internally source IO requests to optimize disk 6. So this is beneficial to my only. Okay, let's go to the third topic. So useful commands and tools. I will talk about iostat and mvstat, profile, SystemTap, and GDB. So iostat shows detailed IO statistics per device. So this is very important tool because in most cases, database server becomes IO bound. So my favorite is to use iostat-x to get detailed statistics. And check read per second. R per s means reads per second, and WS, writes per second, and service time, and util. So IOPS is much more important than transfer size. And always percent util equal R plus R per s and write per s multiplied by service time. This is hard-coded in iostat source file. So in this case, reads per second is 283, and writes per second is 47. And service time is 3 milliseconds, and the util is 99. So, what parameters should I focus? So actually, these two graphs, we use same storage, but reads per second and write per second are significantly different. So sometimes throughput gets higher even though utilization reaches 100%. For example, write cache by quant queuing. So hard disk drive optimizes such that we can gain performance by using these features. In both cases, utilization is almost 100%, but reads per second, right? IOPS are significantly different. So do not trust percent util too much. Rather, it is better to check service time rather than util. So in the above case, service time is 3 milliseconds. In this case, service time is less than 1 millisecond. So if your storage can handle 1000 IOPS, then service time should be less than 1 millisecond based on calculation. So you can send alerts if service time is higher than 1 millisecond or a couple of minutes. That's it. So monitoring such service time is good practice. MPStat returns per CPU core statistics. vmstat is popular. Everybody knows vmstat, but vmstat displays average statistics. And it is very common that only one of CPU cores consumes 100% CPU resources, and the rest CPU cores are idle. Especially it applies to batch shows. So if you check only vmstat, top, iostat, or sat, you will not notice a single threaded bottleneck. And you can also check network bottlenecks, IQ and sort from MPStat. So vmstat counts them as idle, so don't trust vmstat for analyzing network bottlenecks. This is an example. So vmstat shows that IO rate is 12%. So 12% seems very moderate, so this does not seem IO neck, but when you check in with MPStat, IO rate was 100%, almost 100%. So this server was IO bound. So use MPStat to identify a single core bottleneck. OProfile is a profiling tool to profile CPU usage from running processes. So you can easily identify which functions consume CPU resources, and supporting both user space and system space profiling. This is actually mainly used by database internal developers, but if specific functions consume most of resources, applications might be designed to skip calling them. So, and this is actually not useful to check raw CPU activities like IO bound, rows, or mutex states, etc. So we can use very easily so OP control start, benchmarking, OP control dump, OP control shutdown, the OP report. This is an example. So when I tested, the top CPU consuming function was a string copy. And my WC, MB Latin 1, and my UTF-8 unit was shown as a top list. So you can see quite a lot of CPU resources were spent for character conversions, in this case Latin 1 to UTF-8. So probably we can guess that character conversion happens. So disabling character conversions on application side will improve performance. So you can take action to disable character conversions on application side. After disabling, so these string copy on UTF-8 Latin 1 was diminished. So in this case, I got 20% performance improvement in this case. The SystemTap. SystemTap is a scripting-based profiling tool. It is close to dtrace. So SystemTap script runs as a Linux kernel module. So this hooks function calls and profiles. So no need to rebuild applications to profile. And this is supported in Red Hat Enterprise 5 by default. 5.4 is more stable than older versions. Be careful about bug reports. And user-level functions can be profiled if a target program has a dwarf debugging symbols. So MySQL official binary has a dwarf symbols, so you do not need to rebuild MySQL. So you can profile MySQL by SystemTap and dtrace. And you can write custom C code inside the SystemTap script, but I don't recommend because this is very dangerous. So this easily causes kernel panic because no security checking is enabled when using writing C code inside the SystemTap. This is I will show two use cases about SystemTap. So one use case is tracking per-file IO statistics. So this is, I wrote a simple dtrace SystemTap script and a Perl script to tracking per-file statistics. So in this case, it displays up to 10 seconds average IO statistics per file, ordering by IO time. In this case, stock.ibd consumed most of these IO resources. So we can easily decide that stock table should be optimized. So iostat provides per device IO statistics, and iotop provides per process IO statistics. Actually, both are not enough for MySQL. So we want more detailed statistics. So per file IO statistics is much better than iostat or iotop. This would be helpful. This is sample code. So writing probe or syscall read or syscall read. By writing this, when read system call is invoked, this function probe is invoked. Its exact name is MySQL. The counting how many records, how many bytes were read, and which file descriptor was accessed. So we can track how many bytes are read per file descriptors. And writing a timer probe. So in this case, timer probe is invoked every 10 seconds. So every 10 seconds, by checking for each file descriptors, checking how many IOs happened and how many bytes were transferred, and printing these information to standard out, then pipe to Perl script, then filtering, grouping, sorting, decorating inside Perl. So then we can get such information. Okay. So the second case is a user space profiling. They explain the file sort, execute file sort, and return 100 records. By executing SystemTap script, number of return rows sorted by all algorithms was 10, the new algorithms equal 100. So these statistical information can be returned. So the time is up. So we can get statistical information. So MySQL side, statistical information are like this. So process MySQL function from this is MySQL function, are from pointers or unpacked from buffers. When these functions are called, the incrementing counters, then and then in the end printing these numbers. So we can easily identify which functions are called how many times. Okay, so time is up. So I will publish the GDB slide, this slide in the slide share. So please check. What? Do you have me? Okay. So this is the last session. So I'm extending time. So say 5 or 10 minutes. So okay, give me 10 minutes. So GDB is a debugging tool, but GDB has a functionality to take thread stack dumps from a running process. So similar to slice class. So this is very useful to identify where and why MySQL hangs up and slows down, etc. You have to read MySQL source code. The debugging symbol is required on the targeted program. So GDB case study. So in this case, suddenly all queries were not responding for 1 to 10 seconds. So checking slow query logs, all queries are simple enough, but these begin or prepare in these queries are simple enough, but these queries were kept waiting for 10 seconds. This is very strange. So, and CPU utilization was almost 0, and show global status, show full process list was not helpful in this case. In such cases, so using GDB to take thread dumps is helpful. So taking thread dumps with GDB, attaching running MySQL, then taking a thread dump. So thread priority, detach quit, then run GDB. So taking thread dump, analyzing each thread, then which mutexes were waiting. So checking, then reading the MySQL source code. For example, in this case, these functions are blocked. So read the source code, then log thread count are blocked. Then reading MySQL source code, which function locked to this mutex. Then analyzing this. Then, sorry, I'll publish this slide later. So in this case, the thread cache size was the issue. So by increasing thread cache size, the mutex was released very quickly. So such a source code hacking is very helpful in this case. Okay, so this is the final slide, so configuration summary. So install at least tmpfs, iostat, and sysstat packages, and all profile, GDB, and SystemTap are recommended. And allocate swap space is recommended, and set VM swappings to 0, and use all direct. And changing IO scheduler, deadline, and move. So file system tuning is important. And at that point, so make sure to allocate separate database partitions from root partition. When database size becomes full, it shouldn't affect VM commits, which is recommended. So setting limits conf to handle lots of file descriptors, and setting restart VMs if kernel panic happens. This is helpful on HA environment. So in some cases, even though kernel panic happened, MySQL doesn't shut down. So heartbeat doesn't take over. So by setting panic on oops 0, then when kernel panic happened, MySQL restarts, so heartbeat can take over services. Okay, so thank you for attending this session. So the slide will be published very soon. And I will have a session tomorrow about indexing, and SSD session I will present on Thursday. So thank you very much for attending.